Good morning, everyone. My name is Zhang Yingbo and come from PolyU, the Hong Kong Polytechnic University. And my topic is optimal design of data center cooling system concerning progressive loading and life cycle energy performance. And my presentation is divided into 4 parts. First, I will introduce background, then the methodology, then I will present some results, and let's give some conclusions. Data centers is kind of energy-intensive buildings, operates 24 hours every day. Global electricity use of data centers in 2021 was about 300 kilowatts, accounting for 1.5% of global electricity. And cooling energy accounts for about 30% of total energy consumption. Water-cooled multi-chiller cooling systems are widely used in data centers due to their high system reliability and wide applicability. In data centers, the IT load is not static at design load, but experience a progressive loading increase over their lifetime. And the actual start-up load typically is around 20% of design load, gradually increasing to an actual load of approximately about 60% of design capacity. And a rough estimate is the average cooling system COP over their life cycle, and the progressive loading condition is around 3 lower than the design system COP. So the research gap is as follows. Most data centers don't operate at their design conditions and the best efficiency over their lifetime. And optimal design of the cooling system concerning progressive loading is necessary, such as capacity combination and the number of cooling units and optimal loading of each cooling unit. This is a baseline scenario. According to a real case, total design cooling load is around 16 kilowatt, and this system includes 4,000 chillers and 4 chill water pumps, 4 cooling water pumps, and 4 cooling towers. And this table shows some equipment and their design parameter and quantity. This slide shows the schematic of multi-chiller cooling system and the schematic of a cooling unit. Each cooling unit includes a cooling tower, cooling water pump, water side economizer, chiller, and a chilled water pump. And this slide shows the cooling system model and the mathematical formula. So how to design an optimal cooling system concerning progressive loading. And according to the loading profile, we know the total design capacity, progressive loading profile, and we know the life cycle and each period. Then we can develop a cooling system model according to performance of cooling equipment and using a typical control algorithm and according to weather conditions. Then we can get the results of cooling system performance versus ambient air temperature and power ratios. Then we can develop a optimization problem. The objective is to maximize the operational efficiency, and the constraints include total design capacity constraints, and two-set chillers and chiller power ratio constraints. Then we can get the results, the optimal number, capacity, loading of each cooling unit, and the improved cooling system COP, and also the cooling energy savings, total cost savings, and PUE reduction. This figure shows the schematic of the procedure of the design of optimal cooling system. Here's some details, the objective and constraints. This slide shows the results, the energy performance of data center cooling system and the different ambient air temperature and power ratios. The left figure shows the operation mode and the different ambient air temperatures and power ratios. The right figure shows the cooling system COP and the different air temperature and power ratios. And we can see the partial free cooling decreases and power ratio decreases due to the low chilled water return temperature and the low power ratios. And also, cooling system COP is highest when the system is under design condition, decrease when power ratio decreases. And this slide shows some details about economic analysis. Figure shows the chiller cost. The capital cost decreases as chiller capacity increases, but tends to flatten out. And in cooling system, chiller accounts for about 50% equipment total capital cost. And this slide shows the optimal capacity combination and the different number of cooling units. There is highest cooling energy savings when the number of cooling units is 7, but their capital cost is also the highest. Overall, when the number of cooling units is 4, there is the lowest total cost, including capital cost and operational cost. This slide shows the optimal capacity combination and loading concerning total cost. When the optimal number of cooling unit is 4, we can get the optimal capacity combination as follows, and also the optimal loading of each cooling unit. And we can see the optimal capacity combination and loading enables each cooling unit to operate at its nearly highest efficiency. And this slide shows the results about free cooling hours. We can see the average free cooling time is reduced by these values under the constant pressure setting control strategy, and this value under the near optimal pressure setting strategy. And the cooling units switch from low power ratio operation to high power ratio operation. This slide shows the energy savings potential under constant pressure setting strategy. Left figure shows the global cooling energy savings ranging from 13% to 22% depending on climate conditions. The right figure shows the increase in cooling system COP compared with the baseline, ranging from 0.7 to 2.9. And in cold regions, there is higher system COP increase and more cooling energy savings. In addition, the total cost can be saved around 7 to 10% in different climate conditions. This slide shows the energy saving potential and the near optimal pressure setting control strategy. Left figure shows the cooling energy savings ranging from 4 to 9% depending on climate conditions. Right figure shows the increase in cooling system COP compared with the baseline scenario, ranging from 0.3 to 0.9. And cooling energy saving, and we can say cooling energy saving under the optimal pressure control strategy are lower than the constant pressure setting control strategy. And the improvement in cooling system COP is not as substantial as that under the constant pressure setting strategy. And this slide shows the global POE reduction. Can see the data center POE can be reduced by 0.02 to 0.1 under the constant pressure setting control strategy, and these values under the optimal pressure resetting control strategy. And reduction in data center POE is closely related to the cooling energy savings. And this slide shows the total cost savings. We can see there are near 10% total cost savings under the constant pressure setting control strategy and near full average 8% under the optimal pressure resetting control strategy, depending on climate conditions, and is primarily attributed to the reduction in cooling energy savings. The total cost savings are relatively constant across climate zones in both strategies, as the capital accounts for nearly 1/3 of the total cost. So there is some conclusions, and thank you very much. That's my presentation.
Thank you. Any questions? I actually had a great question for data centers.
Okay.
It's also used, robotics, they don't use it, right? Either alternative now. Or this is a pipe.
You mean these two strategies?
Yes.
These two strategies are two typical strategies used in this cooling system. So I propose a optimal problem, and they can be used under these two strategies. And the results show under these two strategies, all have significant cooling energy savings.
Any other questions? All right, well, thank you very much.
Thank you.
We have the third speaker. Pardon me, you go for. Okay.